Alright, welcome to episode 47, Recursion to Catamorphism. So this is a test to see how many people watch far enough into the video where I explain what a catamorphism is, how many people are interested in continuing to learn about it, even if we use a big scary word like catamorphism. But it's really quite simple, so stick with me. And that is, 22 seconds into the video, so I'll know how many people watch past 22 seconds. So let's look at what we had yesterday with episode 46. And yesterday we started with an imperative loop through the thing, through an array to be able to define map, and then we refactored it into a purely functional version using recursion, and it ended up looking like this. And we proved that it's the exact same thing. The result of our map is the same as the map that was imperative. But what's interesting here is that we can also use this same kind of a thing. We could have written this in a different way too. So let's look at another way we could have implemented this to also be purely functional. And in this case, the recursion we won't actually have to deal with. We'll leverage another function and actually be able to deal with it. And that's where catamorphism comes in. So in our map here, let's look at our arguments to this function. We take a mapper, which is some function from A to B, right? And then we take an array, some array of A's, and we return back some array of B. In this case, we do accept this additional optional accumulator that would sit right in here. Let's just say we might have an accumulator there. I don't know that that's exactly the way that we would want to deal with that, but and then there are, of course, parens around these guys here. So that's what we're saying. And if you look at it, if we squint and ignore that, then what we have here is the definition essentially of what a functor is, except that it's specifically for an array rather than saying for any functor. But you don't have to understand that to understand where we're going. I just bring up the fact that we still match with all of our type signatures. This accumulator is just a thing for handling tail call optimizations. And if you don't know what that is, that's perfectly fine. We may go into that later, or whatever. That's a tuning technique here. So if we look at those function arguments that we have, and we go down here and we use this other function. If you've heard of the term map reduce, or if you've used reduce, then you've kind of been able to do this same kind of thing. Because as it turns out, we can write map in the form of reduce. We can also do this exact same recursion here. This is kind of an explicit way, an explicit recursion technique that lines up exactly with what reduce is. And this big word that I talked about, catamorphism, well, basically that just means reduce. But the thing is that reduce is what it's called in JavaScript. It's called different things in different languages. As far as morphisms and into category theory, that would be called a catamorphism because we're going into, think of like cata as in catacombs, we're going into this structure and we're performing some sort of morphism. We are morphing it into something else. So what does that end up look like, and how do we get from one to the other? Well, as it turns out, there's lots of little neat patterns that occur here. So the first thing that we're going to pass here is a mapper. That's our function from A to B. Well, that's the same as here, so we're good there, right? That makes sense. And then we're accepting some sort of an array, which is exactly what we're doing here. It's just that we're destructuring it into the head and then the tail of the array. And in this case, right here, we don't actually pass our accumulator, but what we do is in accumulator, or in the second argument to reduce, is this empty array, which matches with this accumulator. So all of these things are kind of matching up, right? And then, typically with this, you'll see this known with reduce. Most of the times you'll see this be the previous and the current. I've modified those slightly so that they match up a little bit better. But if you look here, we have ACC, which is just an abbreviation for accumulator right here. And then we have the head of wherever we are in the list, which matches up with our H here. And so then what goes in the body of this reducing function here is the exact same thing that we passed as the updated array into this recursion thing of map. So you see it's actually performing the exact same thing. If we run it, we get 2, 3, 4 here, we get 2, 3, 4 here. Everything's the exact same. So what I think is interesting is that typically with recursion, you'll have a base case, which is this accumulator open brackets here, so empty array in this case. Well, you have the same thing with reduce. You have the default case. And then you have whatever you're going to do you're going to do some sort of a function here. That's right in here. If you are doing any sort of React or Elm architecture, you'll notice this as an update function or a reducer. They even call it reducer because it's the function that comes into reduce. So it's going to take the same thing. If you think about it, you have your current state, you have some operation to perform, and then you return a new version of that same state. And so that ends up working very, very similar to, in fact, it is the exact same thing as the reducer with Redux. So there you have it, really. I just wanted to show that this is the same thing again. You can write it with, the cool thing is, so that both of these are purely functional. This is purely functional. This is also purely functional. It's really up to you as to how you want to do it. But it ends up doing basically the same thing, right? So we're purely functional, defining map on arrays, and you see how the things line up. So play around with it a little bit. One thing that's interesting is here we don't have to deal with this goofy destructuring. We do have to kind of cons the mapper H onto the accumulator here is the same kind of thing. But it's basically the same thing. So there you have it. One other way to deal with that, and maybe you learned a new term in catamorphism. Don't be scared of that term now. You know what that means. A catamorphism is just anything that you're going to deal with reduce. So this would be a catamorphism over arrays. Thanks.